Alrighty, so we are back with finishing up logistic regression, and I think you're going to enjoy this. This is one of my favorite parts of the entire semester, and that's actually running the logistic regression on the data set for the passengers on the Titanic. So that's a lot of fun. All right, so just a quick recap before we jump into the code. Very, very small recap. Um, what we've done up till now is work through the ways that the gradient descent would be different for linear regression versus logistic, and it turns out that it's exactly the same, except that our hypothesis function differed. Whereas the linear regression used just a theta transpose x, the logistic regression, the hypothesis function is your sigmoid function with the theta transpose x as the argument that gets passed to the sigmoid. So that is an outstanding result. And so I'm just going to jump straight over into the code and we can have some fun with it. So let's go over here and then open up the code right. If I can find it. There's the screen. Alrighty. Right there. Alrighty. So very compact. Right up from the beginning, you can see how short this is. It's as compact as the multivariate linear regression. That's because it's pretty much doing the exact same calls. We're going to change things up just a little bit, though, and make some improvements to the code. Every time we're calling these pre-built codes that are calling the functions, we're going to get a little bit more close to what is actually done out in the real world. Although you could run the code here and you'd be perfectly fine for most apps. So let's go through it just a little bit. So right off the bat, everything looks pretty much the same. We're going to import pandas, and then we're going to use the pd.read underscore CSV to pull in the clean Titanic CSV. Before we jump any further, let me show you what that CSV looks like, because that's kind of important. Let's see, I'm going to go here and there we go. Yay, it worked. So this is the same data that you're going to have access to. So this is my version of the Titanic dataset that you can find on kaggle.com, and kaggle.com is, I'll type it up here real quick. Go to an area that doesn't matter. Kaggle.com. If you haven't been there, it is a machine learning repository of data sets, really clever code implementations. They have contests where real world entities post data sets that they're trying to get the best possible accuracy for, and they pay big bucks if you can be in the top 3 or so places when the dust settles. I can tell you that hundreds of thousands of dollars have been won by people who do these contests, but that's not actually the big prize. The big prize is if you place anywhere near the top 3, you're going to get job offers that are extremely well compensated. We'll just put it that way. So, anywho, this is what the data set looks like. We don't actually have kaggle.com as an entry here. So the first is the passenger number. We're not actually going to use that, but it's here just in case you need to reference passenger 4 versus passenger 122. And there are, let's see, how many data points in here? So roughly 890 data points. They couldn't get all of the passenger information because some of it was incomplete. So if it was missing the age or the fare or anything like that, I removed it from the data set because I only want to use the ones that we have full data on. 890 is plenty for that. So, if we'd had 30, I might have incorporated a few that didn't have all the data. But since we have 890 full complete data entries, there's no point in just taking out the ones that are missing anything. So passenger number not going to be used. The category that we're sorting into is called survived. So the survived, I guess you call it a variable. This is what is going to sort the data into the two categories. It's a 0 if the person didn't survive, and it's a 1 if they did survive. And I hope everyone is familiar with the Titanic. It's the unsinkable cruise liner that wound up sinking because they hit an iceberg. Uh, I'm sure everyone has heard about the Titanic before. But anywho, so 0, they did not survive the Titanic, the wreck of it, and 1 they did. P class is the passenger class. It has 3 levels: first class, second class, third class. First class was the highest class of passengers, and those were the ones that had the very large staterooms and suites. Second class was kind of the medium income passenger, and then third class was the lowest income passenger, where they were put up in bunk beds, basically, in steerage. So those are the 3 classes of the passenger. Age, self-explanatory. This next column, though, it needs a little bit of explanation. SIB-SPE. This stands for the number of siblings and spouses that accompanied the passenger on the Titanic. So if you had 3 brothers and sisters and you were accompanied by your spouse, there would be a 4 in this column. A lot of people didn't have either a sibling or a spouse, so there's a lot of zeros in this column. The next column is also kind of that sort of makes sense. The siblings and spouse. To be completely honest, there's a rationale for sorting people into that category. I'm sure it's a how to say that. It's not I'm not even going to touch that. They sorted it this way. I'm going to leave it like that. The next category is par ch. So that is parents, the number of parents that were with you, and or children. So again, if you had both parents and 3 kids with you, you would have a 5 in this column. What I'm curious about that I'm not going to talk and try to really reason through is why there's a different column for siblings and spouses versus parents and children. I guess direct descendants versus not direct descendants. I have no idea, but that's the way that the data set's broken up. The fare is actually, I'm impressed that this data was available. This is the actual cost for the ticket on the Titanic. They don't always correlate to a larger ticket being a first class passenger or a low ticket price being a third class passenger, since the fare also includes how many stops the people are going to make. So ticket price went up if you went on all of the stops, and then went down if you only had a single direct stop, straight across the Atlantic. So the next category is male. It's a 1 if the passenger was male, a 0 if the passenger was female. And then the last 2 columns have to deal with the points of origin for the passengers, where they embarked onto the Titanic. So where they boarded. So the Q is for Queenstown, Ireland. The S is for Southampton, England. And then there's a hidden category over here. That's a C, and that's Cherbourg, France. So the way that it went was the initial passengers boarded at Southampton, England. Actually, you know what? Let me draw that. It's until you see it, it's hard to picture. Alrighty, so let me go with take that off and that off, and go to the blackboard. So I'm not an artist and I'm not a geography person, but you have Ireland, and then you have England, and then you have France right here. And this is the English Channel. So the Southampton right there is where the Titanic started. Then it crossed the English Channel and picked up passengers at Cherbourg, France, and then came around and picked up the last passengers right here from Queenstown, Ireland. And then it was set to go to New York City in the US. And so, of course, it hit an iceberg before it could reach New York City, and that's where, all the passengers that died lost their lives. So let's go back now to the Excel. All right, so if there is there's only a 1 in one of the columns, should only be 1 1. That's where they boarded the Titanic. If they boarded at Queenstown, there's a 1 there. If they boarded at Southampton, there's a 1 there. If they boarded at neither places, if they boarded at Cherbourg instead, there would be zeros in the Q and the S column, and that's enough to describe the data. So there's either a 1 in one of them, or they're both zeros, which means there's a 1 in the hidden category of Cherbourg. So there you go. But it's not needed, since if there's zeros in both, then it's implied that Cherbourg was where the passenger boarded. Alrighty, so that's the data right there. It's been cleaned up, hence the clean Titanic data set. One of the things we may tackle if we get further in the semester, if y'all want to, we can actually walk through cleaning up some really messy data sets. It's tedious, and a survey was put out, I want to say it was last year, maybe the year before, for data scientists, asking what they spent their time on. Half of their time was spent cleaning data. Half. That's ridiculous. So, if you want to be a data scientist, a very large chunk of your time will be spent cleaning up data sets, which it's not fun at all. That's the only thing, the downside here. So now that you've seen what the Excel spreadsheet looks like, let's go back to the code and talk about that for just a little bit. Alrighty, so here we have the code again. And so we have the CSV is being read in. It's been stored in the variable text. And then, just like what we've done before, we are assigning the features to X and the outcome, the category predictor, to Y. So survived is the Y variable, X holds all of the others, okay? And those are the column header names. So that so far is identical to what we have been doing, except for one minor change. I don't know if I've mentioned this or not. I can't remember. If I have, I apologize. I'm going to mention it twice. When you look here, the features are getting stored in a capital X, but the outcome is stored in a lowercase y. Why is that? Well, it's because the features are being stored as kind of like an internal spreadsheet. It's a matrix with lots of columns and rows, but the output is being stored in a single column vector. So that's why matrices are normally denoted with uppercase, and the y is lowercase, since it's just a column vector. All right, I think I have mentioned that before, but now you've heard it twice, so yeah, it'll stick extra well there. Now, everything else has been pretty much as what we've seen with the multivariate, but now we're going to introduce something that's different. And this is what will be done for the rest of the semester. It is the default that's used out in the wild, and it's absolutely excellent. We are going to be importing from sklearn a function called train test split. Train test split. Okay. This is the function that you'll use most of the time in order to split your data into a training set and a test set. So it is very robust. It randomizes its choices. It handles everything in the back end. You don't have to do anything. You just call the train test split. You pass it your X and Y and set what percentage of the data you want to be used as training and which percentage you want it to be used as test. So let's actually dig into this just a little bit and talk about it. So I'm going to go to right here. So right here, we're just importing the train test split function right here. That's all we're doing. Down here, we are actually calling the train test split. I'll space that out. Alrighty, so this is the actual function call right here. Train test split, we pass it the X variable that we assigned all the features to. We pass it the Y, which holds the outcome. And then we have to pass it a parameter called test underscore size. Test underscore size is the percentage of the data that you want to be held back and tested against. So this is holding 30% of your data back to test against. 70% will be used to train with. So it'll train the model with 70% of the data and then test versus the remaining 30% that was held back. All of this is completely random too. It's not taking the top 70% to train and the bottom 30 to test with. It is randomly choosing data points, which makes this a much better method of training and testing your model. You don't want to just do the top 70%. It has a much larger likelihood of introducing some sort of bias that's going to skew your results one way or the other. But by completely randomizing everything, you're guaranteed that there's no inherent bias just based on position of the data points. Maybe the time of day that you acquired the data, one after the other, or whatever. So, I mean, you could even say we don't know anything about the passengers except they have a number, but maybe those numbers came from alphabetically sorted data. And if you trained in the top 70%, maybe there would be a skew one way or the other. Maybe the people that were very wealthy tend to have names that started with the letter A. Don't know, just saying. This avoids all possibility of bias based on position within your data. Alrighty, so that's what this function is doing right here. It is taking the three arguments, your features, your outcome, your output, and you need to set the percentage you want to hold back for testing against. It runs this and then assigns the results to these four variables here. Okay, so it takes the percentage of data that you want to train against, that the features for that set for those data entries, and stores them in X train. Okay. It then takes all the remaining features, all the remaining data points, those features get stored in X test. Then it does the same thing with what the outcome, the training outcomes, and the test outcomes in Y train and Y test. So let me kill this and then show you what I mean. I can, where are we? There we are. Okay. So let me clear this. And let's actually talk about it. So let's say that we have, oh, I don't know, something like, I'm making this up, so bear with me. Maybe we've got x1, x2, x3, and we'll even put y right here. Okay? So we have some data. Okay? And we're going to say maybe 0, 1, 1, I have no idea, 0.4, 1, 1, 2, 0.3. I'm making this, these numbers mean nothing. Just doing this to show you an example. Not 2, my goodness, that would be weird. Another 0, 1, 5, 2.7, 0, 0, 7, 2.3, 1, 0, 0, 0.5. All right, so let's say that you have these 5 data entries, okay? And you do the test size. You set your test size to see 0.2, okay? So 20% of the data is going to be held out for testing. 80% will be used for training, all right? It's going to randomly select. So let's say that it selects. I'm going to use a different color. So for the, we're going to say that the training examples are in green and the test example is going to be in orange. Okay. Now I will do one last thing, just it won't actually be used, but this is number 1, number 2, number 3, number 4, and number 5, just so I can reference them. All right. So when you call the train test split, it is now going to take 80% of these, so 4 out of the 5, and pick them at random to train with. And let's say that it picks maybe this one, maybe this one, and then this one. Alrighty, so it picks those 4 to train with, and then it will pick the 4th one as the test case. Alrighty, now when it does the split, it's now going to sort those results into 4 variables. So the 4 variables that we're going to be looking at are going to be, make sure, let me check this, xtrain, xtest. So let's go with, yeah, that's a nice color. So xtrain and xtest. Okay, so what does xtrain, what will that receive? Well, xtrain will receive, let's see, yeah, I guess I can do it like this. Example number 1, x1, x2, x3. So this is 1, x2, x1, x2. If I had good sense, that'd be dangerous. x1, x2, x3 from that. Then second example, x1, x2, x3, whatever those are. They're up there, but I don't want to write them. They'll receive the third one, x1, x2, x3, and then the 5th one, x1, x2, x3. Over here in xtest, it's going to be holding the 4th training examples, x1, x2, and x3. Okay? Now, let me go to another color. You're going to have, yeah, I think I can put it in right here. Oh, almost did that. Almost did that. So it's going to be y train. What does that hold? Well, from the first example, it has y. Second example has y. Third example has y. And the fifth example has y. Okay? What does y test hold? Y test holds from the fourth example, the y. Okay? So it randomly sorts them into test examples and training examples based on this percentage. And it is important to remember that it's holding these values, all of these right here, are held until after training has been done. They're going to be used to test the model against. These right here, all of these, are used to train the model. Hopefully that makes sense. Okay? So it splits them up, says this training example, this one are for the training, and then the remaining whatever are used for the test. Then it takes all of the features from the training examples, puts them in X-train, takes all the outcomes in the training examples, puts them in Y-train, and then does the same thing for the test for the X test and the Y test. Except it doesn't use these to train with, it uses them to test versus. I hope that makes sense. It splits it into, it randomly picks the training examples that it's going to use to train, randomly pick, then the rest of them are going to be used to test with. All the features from the training examples go to X-train, all the outcomes go to Y-train, and then it does the same thing with the test examples. The features go to X test, the outcomes to Y test. Now, the only thing I'm going to say that's in addition to this is these are matched. It knows, it keeps the order the same. So in its arrays, if you looked at the arrays, X-train's very first example, this very first example here, matches the very first example in Y-train. So it keeps the order so that you can tell them apart, so that it knows which outcome goes with which training example. Same thing, like this set of features has this outcome. It always keeps the order the same so that it can reference them and make sure that they're matched together. Alrighty? Even though they're in separate lists, they are matched. Their order is exactly the same. Okay. Whew, a lot. Well, let's go back to Spider and the code. Okay, so it has taken our data and split it out into X-train, X-test, Y-train, Y-test. And yes, you have to put it in this order or it won't know what it's doing. Then we're going to call the linear model again and import the logistic regression algorithm. And it makes sense that it would be stored in the linear model because it's exactly the same as the multivariate linear regression. It's just the hypothesis functions are different. Alrighty, so it then it picks the solver that's going to be used, liblinear, which I think we've used before. It's going to store that that type of solver in the log model variable here, and then it's going to fit the data. So it's going to do log model.fit xtrain, comma, ytrain. So it takes all the features from xtrain and then matches them with the outcomes in ytrain. So it uses the xtrain features to make a guess, compares that guess versus the actual values in ytrain, and sees how it did. And remember, for logistic regression, it's sorting it into one of two categories, either a 0 or a 1. If it makes an incorrect guess, it is heavily penalized because of that log likelihood function. So it really wants to come up with a decision boundary, a line through the data that's going to sort the data into two groups that lets it accurately categorize them. So that does all of the training of the model right here with this log model.fit. And now that the model has been trained as log model right here, we're going to use that in the next one to try to predict values, the outcomes from the test set. So it is going to use the model that it trained in line 23, this log model, and it's going to make predictions on the groupings based on the features in the test set, which is X test. So it's going to store all of those predictions in y underscore pred. We could have called this prediction. We could have called this whatever, predicted values. But y underscore pred tells you that it's the predictions for the y, the outcomes. So we feed it the features from the test set, and it makes predictions on the outcomes. Okay. Then we're going to import some metrics from sklearn that's going to do all the comparisons and give us an accuracy behind the scenes without us having to do any of that. And that is called right here with this bit right here, metrics.accuracy score. And it's going to compare y test, which are the actual outcomes that were held back in the test group, versus the predicted y's based on running the model for the test features. Okay, and then it's going to give us a percentage accuracy. So we're going to run that. Let's come up here and run it. And we got an 82% accuracy. Not bad. It's not bad at all. It's actually pretty high to be able to tell whether or not someone lived or died on the Titanic based on those columns of data. So let's run it again. 0.8. 0. It's different. I sent it the exact same data set. Why am I getting a different accuracy? I'm getting a different accuracy because it is randomly selecting the data entries to train on and then putting the rest to test with. So it's going to pick a random assortment of them. Sometimes it's going to have ones that correspond, that are more accurate to the overall trend of the data than other times, than different times. So every time you run train test split, you call code that uses train test split, you're going to get a different answer. It should cluster around the same value. Like if I run this several times, 0.82, 0.80, 0.80, 0.80, 0.82, you can see it's somewhere around 80, 81 on average. It's still much better than chance of 50%. Alrighty, now I didn't go over something that I want to show you. This is going to be something I want y'all to do. Notice that up here, we assigned all the features, and then I had this one line that was commented out. You comment something with a line of code out of your code with the hashtag. So, my gosh, I've got a giant kitty cat that just jumped up onto my table. Kitty, kitty. I'm going to go down there. Sorry about that. Giant cats are giant. So this one that I commented out only has P class enabled instead of all the others. So I just gave this as an example so that you would be able to look at predicting based on 1, 2, 3 columns or all the columns and see how well it does. So if I comment out where it's doing all of them and take out the little hashtag and from this, now it's only going to train on the P class features. Let's see how accurate it is with P class features. So here we go. 69%, 72%, 70%. So it's not as accurate as predicting who lives and who dies. It's still better than random chance, which saying that the class of ticket had some influence on whether or not you lived or died on the Titanic. But we can now change this to be anything. Let's look at age, see if age was a big factor if you lived or died. So we do age now, 58, 61, 60. Not much better than random chance. A little bit, but not a whole lot. So age didn't have a whole lot to do with whether you survived or not. Did the number of siblings and spouses matter? Sibsp 58, 66, 61, 66, 63. A little bit, but that was not the main determinant. So what I want y'all to do is run through these one at a time and see which one was the most accurate predictor at determining whether or not a passenger lived or died. One of them is definitely the most likely to predict. Probably already guess which one that is. So just run these and see what you get. I hope you enjoy playing with this, and you can also do combinations of. I could add a whole nother one if I wanted to add age here. I could do it like so. But you can do this however you want. It's completely up to you. This is not the best way to figure this out, but this is a good way to just play around with the code and kind of have some fun. So I think that is about it. If you have any questions, just send me an email. I hope you enjoyed this. This is one of the ones that we're starting to get into more powerful algorithms that are used a lot. And logistic regression is one of the ones that is constantly being used. Sorting things into categories, yes or no, is huge. So play around with this, see which one of the categories is the most likely, the most powerful, accurate predictor for whether or not someone survived. And I will see you later. Y'all have a wonderful, wonderful day. Bye, everyone.